Yes.
Hi, everybody. Welcome back to the Astro Imaging channel. It's good to have you all back. It's Labor Day here in the United States, and it's a 3-day weekend. And last night we were out in the desert at our observing site, and for some reason there was a fireworks display about 1.5 miles away at the local park, and it was beautiful. You know, just off on the horizon, kind of the fireworks going off and everything. And we had a great night of imaging and stuff. We're going to have a great night again tonight. Adam Block is here. Adam wants to tell us about new gradient processing script in PixInsight, and he's worked pretty hard on getting stuff ready to tell you. He really believes in this. It's going to be a little more technical sometimes than Adam usually talks to us about, but he'll be talking to us about that kind of stuff, and so we're looking forward to that. I want to catch you up on what's happening on the Astro Imaging channel upcoming in the next few days. So there's my calendar. Adam's here tonight, and Glenn Diekman's coming in next week, and he's going to be talking about imaging through the light dome. And he takes a lot of really nice pictures from his backyard in suburban Los Angeles. So he's going to be doing that. And then Queeve, the lazy geek, is coming to us. Wanda did a good job of sweet talking him into coming on to the show. And we had to pick a peculiar date, September 19th, because he lives in Tokyo and he has to work. But Monday, September 20th is a day off, so he can come and visit with us. And he does a lot of really good videos, and everybody likes his shows, so you should enjoy that. And then we've got something really different the week after that. Peggy's going to tell us about how to take our astro images and use them to help blind people, how other people have helped use the astro images to help blind people, transfer them into different media so that they can enjoy the wonders of the celestial skies. Then we're coming back with Linda Thomas Fowler, and she's also going to be talking, it's curious, 3 in a row, and then there's a 4th one down here, all about imaging under light polluted conditions. So we've got a lot of good stuff planned. As you can see, we're planned all the way up through November, but we don't have anything, I don't think we have anything yet in December and thereafter. So we still need people to hit the contact button and tell us your name and help out by presenting. Remember, you can present this stuff. Yeah, we got a lot of good astro imagers here, and we do what we can do to present for you, and we do a lot of work to get other people to come in and present for you. But you too can present this stuff. Several of the people you see coming up in the next few months are members of the Astro Imaging Channel Club. They meet with us every Sunday, and they decided to take a shot at making a presentation. So we'll be glad to see them. Now, there's a couple of places, a couple other things we've got to look at. We already have a couple of people that have entered, that have worked on Eric Cole's data, and you can get Eric Cole's data by going to the TAIC workshop and link it to the data files, and you can download all of the data files for Eric's M33, and then you click here to submit the file. And then when we get them, we'll schedule a show where we can look to see how you treated that data. That'll be up October 17th. We hope to have that show. Things can change, but that's what we hope to do right now. And Arno is at work. Where is the tech shots? There they are. If you look here, we're doing nebulae right about now. So if you've taken a picture of a nebulae sometime between November 1st, 2020 and October 31st, 2021, please submit them by October 31st, and we'll make a movie out of it like we've done before with some of these and show off some files. I know we've got a number of people have already submitted some nebula, and they're pretty good work. So please take part in that. Okay, enough of the preliminaries. When we were talking before the show, Adam said that he was going to reduce all this to a really good video and stuff like that, and he makes great presentations, great tutorials, and things like for people to find out about processes and how to image and stuff. But we've got an advantage over his tutorials is that we can ask him questions as we go along. So so right over here, you should be getting ready to ask a bunch of questions to people, to Adam, and go ahead and say what you have to say about his presentation. If you have any questions, be sure to put it in there. This is something you can't do when you're just watching one of Adam's tutorials. Okay, enough of me. I'm going to stop sharing. I'm going to stop sharing as soon as I figure out how. And take it over. Adam, tell us who you are and what you want to talk about, and tell us about that new process.
All right. Thank you very much, Alex, for the introduction, and obviously for another opportunity to speak here in the Astro Imaging channel. I enjoy these opportunities very much, and in this particular case, it's something that's special to me because it's a subject that I think is really an important one, and it's one in astrophotography, in the processing of astronomical images, that just doesn't get as much attention as I think it should. So today I'm going to be talking about the concept and the process of normalization of images. It's something that is necessary, mandatory to do things correctly. And there is a new tool in PixInsight that allows you to do this in a way that is better than what is currently available in its kind of default form in the software PixInsight. So I'll be speaking about PixInsight. I'm going to be talking about this new script, which does cool things. But overall, even if you don't use PixInsight, the concept itself of image normalization, why it's important, what it does, and how you can use it to your advantage is something that everyone will be able to take away from, I hope, the information that I'm going to be giving. So that's where I'll begin. You mentioned the video, and so I have here on the screen, and someone just chime in and say that everyone can hear and see me. This is my YouTube channel. And I obviously post videos on my channel. One of the most recent ones is another topic that I considered talking about, but it's another technical one. But I do have it's in the 3 parts here, a 3-part video of what I'm going to be talking about tonight. So it's already done. It's true, you can talk to your computer, I guess, while you're watching the video, but you won't get too many answers, I suspect. Though I think I did a good job, because when I make one of these tutorials, I really sit down and think about how I want to present it. Now I'm going to be doing it extemporaneously, and I'm just going to be doing it on the fly. But I would encourage everyone to do 2 things. One, watch my cool video that I did on this topic, but there are other topics that might be of interest. And one of the things that's important to me, and I'll just say this because it's just one of my own things, is that the YouTube tutorials that I make, those are the public ones. I'm not going to be a YouTuber. I'm not going to make any money on talking about the normalization of images. The only reason I do it is because I hope people will watch them. And if no one is watching them, it is a bit, that's not cool. I have to have people watching the videos, or it just doesn't inspire me to make them, right? I got to see the numbers of eyeballs watching the videos. So people that are part of the Astro Imaging channel, please subscribe to my website as well, my YouTube channel as well. And you might get more of this astronomy stuff, and it's all related. And so please consider subscribing, especially after watching some of these tutorials. Okay, so enough of that. Now I'm going to get right to the topic of image normalization. First, I'm going to show you PixInsight. There is always this issue with sharing the screen, especially through this kind of forum. I will try to explain as distinctly or as explicitly as I can what some of the options are in the tool, because I know it's very hard to read when you're looking on the screen to see some of these things. This is a script, so it is under the script section, and this is a batch processing script because it operates on many, many images to do its job. But there is a script that's called NormalizeScaleGradient. And the reason it has 3 concatenated words is because it is literally the job that the script does. It is a normalization process by finding scaling factors of images, and it also compensates in some sense matching gradients. And I'll explain what all of that means in just a moment. But this is literally the script here, and I'll show how to use it in a couple of examples that I already have set up. One of the interesting things about this script is it is computationally intensive. It takes some time to take a bunch of images and do the job. So I won't be able to do a large set of images. In advance, I've already done that, and I will show you the results. But in real time, I will show you on a small subset of images so that you can see how it works literally in real time. Where I'm going to begin, though, is at a completely different place, and I'm going to have you look at some colored lines. Looks like a barcode here at the moment. And I think that this, in some metaphorical way, indicates something about the normalization process. If you imagine that each one of these bars is basically an image. So there's this idea that when we take pictures of the sky, the atmosphere controls some of the information that we get. Our optics control some of this information, and so does, of course, the sensor. They each have sources of noise. They each affect how many photons we're going to receive. And so the normalization process is one that allows us to make images similar to one another so that we can do a very special thing. Well, the most important thing we want to do is to identify outlying values, things that are not useful information we can discard, so that at the end of the day, when we average all of these images together, we get only the information that we want. And that increases the contrast of the image. That makes it a cleaner image. It makes it easier to process. All of that is part and parcel to this idea of the normalization of images. So normalization really means making things similar to one another in their attributes. And the attributes in this case deal with the amount of light that you have and the source of that light effectively. So if you imagine, I have these vertical lines. If you imagine that whenever you take a picture of the sky, you have some pedestal value of the sky brightness. The sky is never truly black. It has some brightness. It's darker when the moon is not in the sky, and it's brighter when the moon is up. And then the sky brightness is even brighter when the sun is in the sky, making it not possible to see the stars, at least with your unaided eyes. So the sky always has some level of brightness to it. And that's represented here by the blue part of the vertical line. So if this is one image, the blue part is the sky background pedestal brightness, if you will. And then the other value that I have kind of in an orange beige color would be the amount of information, useful information, signal that we're getting from the objects that we're observing, stars and galaxies and nebula and all the stuff that we want to see with our telescopes. So at the end of the day, we're going to want to average all these images together, and we want to discard anything that are satellite trails, cosmic rays, artifacts, anything that isn't useful to us. We want to discard those and then average the rest of the information. So if you were to look at a data set like this, like I have here presented, you might naively take this set and do your rejection algorithm. You're going to look for values, or you're going to look for images that have outlying values in them where they are significantly different than what appears in other images. If you did this naively right here, we would reject the first image because it appears much, much brighter than all the other images. That would be the naive thing to do, because the only issue is that perhaps all the other images were taken with the moon not in the sky, and here this first image was taken with the moon up in the sky, and so it just has a brighter background. So one part of the normalization is to equalize, is to add or subtract some number to make all of these background levels exactly the same. You can also have the situation where you take pictures of the sky, and again, you want to average all that information together. Maybe it was taken under a dark night. All your pictures, the sky brightness was basically the same. It's not varying, but your signal strength might have varied. It could vary because there were clouds in the sky. It could vary because maybe your exposure time was just shorter. That's not a bad thing. You can combine frames that are different exposure times. The brightness of the sky is approximately going to be the same, let's say, but the signal strength will be different. So again, if I were to combine this information and use some rejection algorithm, I would be throwing out information here that we could choose to include, but we will include it for only what it's worth. And I'll be getting to the weighting idea that is an outcome of this normalization process. We get to weight the images according to what they are worth. Now, the real world example is what I have here on the screen. The real world example is that you have varying levels of sky brightness all the time, and also varying levels of signal. So the idea of normalizing images so that you can subsequently do this rejection algorithm and then combine them all through, in PixInsight, that's image integration. You first choose within your set of images, you choose a reference frame. And that frame is what you compare all other frames to. So you adjust all other frames to match your reference. It doesn't really matter within a set which frame you might choose to be a reference, because the adjustment that you're going to make is all relative. So whatever frame you use, if you happen to use a poor frame, then all of the other frames are going to look like super frames when you make your adjustment compared to the poor frame. And when I say make an adjustment, here's what literally happens. If you have an image that doesn't have quite as much signal, you multiply times some number to make it equal in that level compared to the reference frame. Likewise, if you add or subtract this sky brightness value in order to make it the same as the reference value, and you might think, well, my goodness, if you're making those kinds of adjustments, you know, we're making all the images equal to one another in some way. Then if we combine them all together, you know, what good is that going to do? There was an image here that literally didn't have as much light, right? Well, the thing about this process, especially the scaling thing where you're multiplying times the number, we remember what we did to each image through that normalization, especially the scaling process. And the inverse of that is the weight, effectively, that we're going to be giving it. There's two parts of the weight, which I'll get to in just a moment. But again, the simplest version is if we have to multiply an image by 2 in terms of its signal to equal the reference frame, that probably means, assuming it was the same exposure time, that it was a poor frame. It didn't get as much light because maybe you're looking at half of the dome. Maybe a cloud came in front of the telescope. Whatever it is, you just didn't have as much signal there. So we remember we had to multiply by 2, and that means when we add it into the average, we will only add it in for 1/2 of whatever the reference frame is worth. So that is a weighted mean, and that is the ultimate goal of, you know, not only being able to figure out outlying values through this normalization process, but once we've done that, we can also assign weights to each of the images. So the thing to bear in mind here is that we have this scaling that happens for each. So there's 2 steps of normalization. We have a scaling factor, and then we add or subtract this pedestal value. I want to mention one thing about the add and subtract. The scaling factor, what you multiply for the signal strength, it is a fairly safe assumption to say that for a given field of view through a telescope, unless you're looking like through a 50mm lens or something, the scaling factor in that field of view is probably the same across the entire field of view. So it is okay to have a singular value for whatever the scaling factor is between one image to another. But the background level, that isn't necessarily a single value. I've been referring to it here like it's a single value, but it's not necessarily so, because there are gradients in images where you have across your image a varying level of brightness just due to, it could be the optics, it could literally be something in the sky, it could be a number of causes, right? Your filters, whatever it might be. And so you need to characterize that as well. If we just added or subtracted one number from every pixel to represent the sky brightness, that wouldn't work as well as what the script does that I'll show, where you're actually matching the gradient that you have in your reference image. And I want to stress that really quickly here. This is a matching routine. Normalization is matching images. Not only do we match the scaling between images, but we also match the gradient. So this routine does not remove gradients. It matches to one gradient in one image. And if you pick a good image that has a simple gradient, that makes life easier later. If you don't remove gradients from your images and you convolve them by adding them all together, it is much more difficult to to handle that situation, and that reduces the contrast of your image. So that's the general idea. That's the concept of normalization. And with all of that in mind, now I can actually go into PixInsight and start showing you some images and showing you how it works. Let me show you some images here. I have a data set that it's just an RGB data set that I've taken through the astrograph that I have access to. It's a Takahashi 180. So it has like a 4-degree field of view, a very large field of view, which has varying sky conditions and things because you're looking at so much sky at any one time. So it's a really good litmus test for this particular routine to do its job. And I think the first thing I want to say before I even show you an image is that image integration is the tool. Let me get this out here. Image integration is the tool that is used to combine images. This is the ultimate goal. You combine images when you have them all ready to go. And within PixInsight, the normalization process is built into image integration. It's always there. And the way in which it does it is different than what I'm going to be showing you the script does. So you'll see image integration here has a thing that deals with the normalization. That's what this is about. You select that. Most people just go with the default. And there's also another normalization because of the way that this tool works that deals with the rejection side of things. You also specify, sorry, I should put this on something here, a normalization method for rejection purposes as well. So normalization is built into the tool. I just wanted to point that out. But now we are exporting that. We're now taking this outside of image integration and doing it on our own through the script. So that's where in the workflow this ends up being. You're going to calibrate your data. You're going to register all of your frames. What you would do at that point normally is you would combine everything together. But now we're going to insert. You just get as far as registration of images. Now you put the images through this script that I'll show, and then you do image integration, removing the normalization that is already there. You say no normalization because you just took care of it yourself. That's how the workflow looks like. So let me show you some images of this field that I've been working on. That is not the right folder. Let me get to the right folder here. I've been working on this very dim, it doesn't even have a name, dusty field in Draco. And let's see, what do I need to do? Hold on. I need to go to my registered images. That's what I need to do. So registered, thank you. I have already registered a bunch of frames together. One of the interesting things is I'm going to demonstrate one of the things that I mentioned is that I have 2 different exposure times as well. The data that I took, some of this data where it was 480 seconds, I took last year. And then this past summer, I took more data when it was 10-minute exposures. So there are 2 different time frames that I acquired this information, which is interesting to compare because they are actually 2 different qualities of data. I have already done the work on the blue, but I'm going to, just for fun, open up some red images here and show you what they look like, so you can see what the data looks like here. What is the? Thank you. Now, as I recall, I don't think there are any major problems with this. And again, you're going to look at these images and think there's nothing there. It's really only through the integration of images that you would even see much of this dust that's in the data. So what is interesting here is that this normalization process is super important. By simplifying the gradient and removing all the outlying values and weighting the images properly, you're going to get the possible best results you can. So here is one of the images. I'll make it a little larger so that hopefully it looks like something on the screen. You can probably dimly see here, there's some dust in this field. There's a satellite trail there as well. I've got to display these images in the same way so that when I blink them, they'll look okay. And if we flip through the frames, you're probably in the video not going to see too many differences, but let me zoom out here. And let's see, you can probably, yeah, do you see how the sky changes in its gradient? We kind of have it brighter down here, and then it changes up here. It's partly because there was a meridian flip. Then we'll just probably see different quality of data if we zoom in and zoom out. If I had loaded last year's data, it's even much worse. You'll see that in just a moment. But you can see the varying brightness of the sky. And if we zoom in and we look at stars, there's variations. Some nights are better than other nights. I feel bad about not loading some of the bad data. So let me load some of the bad data here. That's red. I won't load too many, but I'll load some of the less good data.
While it's loading, do we have any questions, Eric?
Yeah, there was one question.
Okay.
Nori asked, are you considering gradients that are the result after the master flat and master dark calibration?
These are all calibrated images that I'm showing right now. This is calibrated. It looks terrible. Look at that. What the heck is that? So yeah, these are calibrated images. It's the gradients that remain after calibration, whatever their source, whether it's your filters, the sky, so on and so forth. They could just be flat errors. Literally, you are introducing a gradient because of your poor flatting that occurred. So whatever the cause is, those are the gradients in the images that we need to compensate for when we do this normalization process. Okay, so I hope you can see that this literally has clouds, or can you see the changes here in the frames? I mean, that looks like much worse data than this. And then if you zoom in, you can see the stars are not quite as pretty, and they're much dimmer and blobbier and whatever here. So it's actually not that bad, but there are differences. So one of the things that I'm going to do next is I'm going to choose a reference frame. We have a set of data, and whenever you do normalization, this applies to a particular filter. So you're not normalizing between filters. It's just one filter, red data, green data, blue data, or something like that. So I'm going to choose in these frames that I have open here, and I'm going to choose from one of the first. I'm going to say that one of these is a great image. Let's choose, I don't know, June 11th, number 7, and there's a reason I'm going to do that. It's because I chose that in the blue. This June 11th, number 7 image. I'm going to say that's my reference frame. That's the one that I'm going to choose to be my reference. I know it's a reasonably good frame. It's not a bad one. It's nice to choose a good one because then it'll have kind of a weight of 1, and all the other weights will be wherever they end up being. So that was it. I cycled through the data. I looked for a good frame, a reference frame. And now I can basically go into the script here and load those frames. So as I mentioned, I'm not going to load them all. I'm just going to load some fraction of them. So this is the red data. Now I need to load my reference, the one I said. But now I'm just going to randomly load some of these frames here like that. And then I'm also going to add a few of the frames from the previous year, which are 480 seconds. I'm going to add, no, I'm in blue. I need to be in red. I'm glad I caught that. I don't know. That's a lot. There we go. Okay, I've added my frames. And in the selection here, let me see what I've done wrong. Hang on. I'm going to do it again. So this one says 480 seconds. Let's randomly pick here. I did that. And now let's go to this better be 600 seconds. And I want to choose the number 7. There it is. Okay. I believe I have it right now. I don't think I didn't switch directories. So I need to choose one of these frames to be the reference, and I have decided to choose the one that was number 7. That's my reference. So the first step is I load the images here. You'll notice that over on the left side, if it is contained within the image in the FITS header, it will show you the altitude. If you didn't even want to blink your images, you could, assuming that maybe you took it under reasonable conditions, just pick one of the images where it's highest in the sky. that might be a good criterion for knowing if it's a reasonable image or not. So that's one way, but I like to blink through the images and just find a nice good one. So I'm going to say set that as my reference. Now, one of the things that this script does is the method by which it determines the scaling factor is to measure stars. And in order to measure stars, it needs to create little apertures around stars, which means it needs to know something about your plate scale, how many arc seconds per pixel your scale is, because that'll kind of determine the sizes of stars, the sampling. So if you don't give it enough information, it'll ask you to fill in the rest of what it needs, 2 out of the 3 possible values here. So that is the correct focal length, and it understands the size of my pixels are 12 microns. So I say, okay, and it loads the reference frame. Great. Now, I'm going to tell it a directory to save all of these files into that it's about to generate. I have a directory made for that. It's currently empty. So that's back to where I was, which is Draco, Adam Draco. Does anyone see Draco? Am I in the correct place? Yes, I am. Where's Draco? I'm blind.
Draco Neb?
Yeah, Draco. Oh, there it is. I'm blind. Okay. NSG, red. Good. So I'm going to save the files there. And for purposes of demonstration, I'm also going to output the gradient files. This will actually show the measured gradients that it measured from the images, which is kind of cool to see. And I'll explain that in just a moment. Let me just go through these things. Most of these things, just by default, are going to work well. But if you look at them in some detail, you can tweak them in such a way to get an even potentially better result. So the photometry stars, I need to select another frame to compare with the reference. You're always looking at 2 images. This is why it's a relative process. So I just clicked on another image there. And the photometry stars are literally the stars that it's just going to measure. And when it says photometry, you can see that it actually drew a little inner box and an outer box. So it measures the flux of a star, and then it subtracts the local background that is surrounding the star, and that's stellar photometry, basically. I can look at either the reference frame or the frame that we're comparing to, the current frame that we're comparing to. There is nothing really to do here as long as it is selecting enough stars, and this has plenty of stars in this image. So there is no problem at all. This uses the same structure detection stuff that PixInsight uses throughout the software. Now, the next thing is the photometry graph, and this is the really cool thing. The photometry graph, what it is doing, and let's see, I can't, nuts, can't show it to you, but I can show you the scaling factor here. The photometry graph is actually calculating the scaling factor between the reference image and the one image that I happen to be looking at here, but this is what it's going to do with every image. So it's calculating this by measuring the brightness of the stars, the ensemble of stars in both images. And if the reference frame has all of those stars on average are brighter than all of the ones in the other frame, you need to multiply the frame that you're looking at by some number to equal what the reference frame has. That's the scaling factor, and that is what is being calculated here in this graph. The slope technically of this line is the scaling factor because you're graphing the number that you had to multiply. So the one number that you're getting in the reference frame and the other number that you're getting in the frame that you're comparing. So the slope of the line is basically the scaling factor. And you'll notice that there's a little option here where you can filter photometry stars if you take off the auto. This means you can limit the stars either at the bottom end or the top end if they are somehow affecting that fit. Now, in this particular data set, I mean, there are so many stars, it doesn't matter. I can imagine that if you only had 50 stars in your image, and some of these super bright ones, because they're saturated or whatever, are not giving a really good result, you can exclude them by, moving the little slider here, and it's hard to see that it's going to do anything, I bet you, in this one. But you can exclude some of these points here. I don't even know, are any of those disappearing? There's so many. Oh yeah, I'm doing the bottom end, sorry. The top end is this guy. There we go. So you can exclude stars at either the bottom end or the top end if they're too faint or if they're too bright, and control this. But this will make absolutely no difference in the calculation of the scaling factor, which is behind my blink window. I really wanted to show that to you. But I know if I exit out of here, I'm going to lose my setup. So I'll do that later. Now, there is one other thing that's really cool here, which is the second step. The first step is what we talked about, the scaling factor. The second step is the calculation of the gradient. It needs to know what to add or subtract across your image. So now that it knows the scaling factor, it knows what it needs. It can just calculate the brightness of each of these little regions in the picture and add or subtract the value compared to the reference frame that it needs to for every little box. That's how you get to match the gradient. But what you don't want to do is have the scattered light of stars and other things affect that calculation of this gradient, so that you exclude stars this time. Now we're not measuring them, we're excluding the very brightest stars so that they don't become part of that calculation. That's automatically done here. Though I'll show you, given some time, an example where we might need to manually exclude a very bright region of scattered light of something, and then it won't affect the gradient calculation. So let me show you the gradient calculation. That's the final little button here. This is showing the gradient, the brightness as it increases or decreases going across the field in one line. Either you can look at a horizontal divide across your image, or you can look at a vertical line. You can change that here with the gradient path. You can either look at a horizontal line or a vertical line. And you can change where you're looking by just shifting this. So this is looking at a different, this is looking at x equals 1136. That's my chip has 3000 pixels, so the middle was about 1500. So this is a different line. And you want the spline fitting. This is actually fitting. It's trying to fit that brightness variation across the frame according to the measured values. You can change how strongly it does that by changing this gradient smoothness here. By adjusting that, it's now recalculating, and you can see that the line got a little bit closer. It doesn't need to be perfect, but you want to try to match this gradient that just goes through the field. There, it's matching reasonably well. Let's look at a vertical line instead of a horizontal line. You can see in the vertical direction, it's matching the gradient very well. So that would be it. That's all you have to do. That is the actual only adjustment that I made. And so I believe I'm going to press go and press run here. Let's see. Do I really want to do it? Yes, I really want to do it. I'm doing it. Here we go. So one second. Let me just point out one more thing, because then you'll know how much time you have to ask the question. As it computes one of these images, it says it takes 11 seconds. Then it can give me the estimate of exactly how long we're going to wait. So in the next frame here, it will tell me I have 1 minute and 50 seconds. Okay, so you've got 1 minute and 50 seconds. Go ahead.
Okay, go. Will this take care of something like amp glow, which is probably going to be present in every image?
So again, we're not compensating for any gradients. We're not compensating for them in the sense that we're not changing them. All we are doing is matching a gradient in your reference frame compared to any other frame. So if you're, now we hope that you don't have an amp glow in a calibrated registered frame. But if your reference frame had an amp glow in it, then yes, it's going to match that amp glow in all other frames. Imagine if it didn't. Imagine what happens if that was not true. If you had a satellite trail run through the part of your image where there was the amp glow, because the amp glow wasn't matched in both images, you're not going to reject the satellite trail necessarily correctly, because the background is not matching in both images. So the rejection won't be as good. That's why this matching is so important. And I'm going to demonstrate that here in just a moment. I've already have the rejection pictures, and I can show you how the rejection is better once you've matched the frames. So we're not reducing.
You're using my question time, Adam.
What's that?
Actually, you're using my question time, and I got a few piling up.
Oh,
So
go
does
ahead.
this mean that when you're all done, you still might go back and do DBE?
No, you have to do DBE, yes. You're going to still have a gradient potentially. This does not remove a gradient. It only matches a gradient, but it might be a simpler gradient. It's one gradient. Remember, if we don't do this, we are adding many frames with many different gradients, and that's a convolution, and that's a mess. Here, we're matching one frame very, very well. If it happens to be a frame that doesn't have a gradient, then that's fine. But something that you may see in a question there, do not apply DBE to make the gradient go away in your reference frame. This is not like normalization. You will make ineffective the normalization process if you are to change the reference frame in any way. So don't do that.
Next question. How is this different from the job performed by local normalization?
That's what I'm talking about. So local normalization is a different process where it examines the field locally at every place, but it's doing it kind of like a mixture of scale and this add and subtract locally. So it's doing multiple scales, scaling factors, if you will, everywhere. And that introduces artifacts. That is not the same as this process. This is a true normalization. Local normalization is more like a fitting of the image, and that one is the kind of thing where you can do a minimization of the gradient beforehand, but it's not the kind of process that you do every time. Local normalization is something you do for problematic images. It's not something that you do every time, and it introduces artifacts if you're not attentive when you're using local normalization. I would not recommend using local normalization in general unless it's a problematic image.
So what if you have a nebula that basically fills the field?
Well, if you recall, when we looked here at the sample generation, this object doesn't have nebulosity. Well, it has some nebulosity, I guess, right? But every one of these boxes, it's measuring. It knows the scaling factor, right? And every one of these boxes, like this box here that has nebulosity in it, it has exactly the same nebulosity in the reference frame. So it doesn't matter that there's nebulosity in both frames. Remember, this is a relative matching process. It is fine that there is signal, be it from a nebula or a galaxy, in these areas. So that doesn't affect the calculation in terms of getting the gradient right. Isn't that interesting?
The last question I have, unless one pops up here in a second, Linda asks, is choosing the image with the largest number of, I guess, visible stars a reasonable reference? Or should you, I had a question that, should you choose it with the least eccentricity, the highest
It doesn't,
half max?
Yeah, you don't, it's not that important. This is a relative process. So the only reason that I would say choose an average or better frame for a reference is because in one of the things that has just gotten spit out, so let me just show it to you, is it tells me the weights of the images. And the interesting thing is that if I choose an image that I know to be a reasonable frame, I can see what the resulting frames are. Just at a glance, I can see what the ultimate image quality is. If I chose a poor frame to be my reference, or some middle frame, half the frames are going to be better, half the frames are going to be worse. It's kind of harder to see just at a glance what the total image quality is. Does that make sense? It's just, maybe that's the way my brain works. So right now,
what about choosing the same reference as you do for your processing? End up with your registered stars. Is that a good rule of thumb, or should you not choose that, or does it make any difference?
I would just, I don't know that it makes a big difference, but I would just blink through the frames so that you can see images, see that they don't have any artifacts in them. You're not looking at some weird gradient in that one image. You probably don't want to use that as your reference. And then, yeah, that it just looks like a good image. I wouldn't give it that much more thought, because again, I hope the point that I'm trying to make here is that this is a relative matching process. Let me say this in a different way. If all of your frames are crap, this doesn't make them any better. This just matches the frames. Now, one of your crappy frames might have only half the signal strength as the very best crappy frame. So it's telling us the relative quality within your data set, but this doesn't tell us anything about the quality of the data set outside of that, external to, say, some other measure or metric. So it doesn't really matter which one you choose as a reference. I just think for ability to interpret the results, it's good to choose a good one.
Okay, I think we're all set for now.
Okay. So on the screen, you'll see that I now have some results, and it tells me that I didn't choose a half bad reference frame because most of the other frames have been assigned a weight that is less than this. So I now need to tell you something about the weighting process. You know that the weight is something about the inverse of the scaling, but there's also a noise term. It is not entirely just the scaling factor. So I just want to bring up the reference here, and this will be the only equation I show, but I just want to show you how the weight is being calculated. And I want to show you why what we're doing now is better than what is currently in image integration. So the weight is calculated as the inverse of the scaling factor, that's the K thing, times a noise term. So there is a way that you measure the noise of the image as well. You square those two, and the inverse of that is what you assign to be the weight, okay? And because this is a square, any error in either of these two measurements, be it the scaling factor or the noise, when you make a small error here, it becomes a big error, if you will, in the weight that is assigned to the image. And so that's why it's critical to get these two terms as accurate as possible. Now, the way that I've just described how the script does it to calculate this K value is by measuring stars. The way image integration currently does it, that's what this document is about, does not measure stars in an image to calculate the scaling factor. To measure the signal strength between images, it looks at another statistical metric that unfortunately has the name of scale, but that's not scaling factor. It's a dispersion of values in an image. You look at all the values in the image, you look at all the variations of those values, and that tells you something about the, it actually is related to the signal of the image, the amount of noise that you have there. And so that's used to be a metric to measure, you know, one image has is a better quality than another image. But here's the point that makes what is currently the default in PixInsight problematic, is that when you have excess light in your field, that gradient that might be in the sky, it is degenerate in noise evaluation. That is this method that PixInsight uses in image integration to calculate the scaling factor. The noise evaluation method does not distinguish in signal strength between a brighter background sky, which could be due to clouds or anything else, and truly the signal of interest. And so what happens is noise evaluation basically gets tricked. It will give perversely a higher weight to a poorer image when the background becomes brighter. Let that sink in for just a moment. That is perverse. When you have an image that, you know, maybe there's a little thin cloud, still perfectly good data, but we want to give it a little bit less weight. Noise evaluation does precisely the opposite. And that's what I don't like. And that's why I'm so excited about this script. And that's what I'll demonstrate in just a moment. Hang on. So now let me get back to here, where we were looking at the weights, right? But let me just hint at what I'm talking about here. One of these frames, let's see, this frame right here, NSG, that is noise scale gradient, normalized scale gradient, says that this is a crappy frame. This frame that is June 12th, number 6. June 12th, number 6, it says is not a great frame. So I will open it up. And then we know our reference frame is the best frame. Well, it's not the best frame, but it is a good frame. Let's see, yeah, it's a good one. So is it true, right? Is it really a bad frame? Let's look. So if we blink, here's June 11th, and here's the June 12th. If we blink the two by comparing, oh, hang on. You know what I really need to do? Let's zoom in. They're matched in terms of their, let's be sure I did the right image. June 12th, number 5, is that the crappy one? I already forgot. June 12th, I said the crappy one was June 12th, number 6. Sorry, not number 5. I have number 5 here. Let's look at number 6. Number 6, June 12th is, how come I don't see number 6? Oh, is this 6? Yeah, that's 6. Okay. There we go. Oh, yeah, look. Look, it's already, you can already tell it's got weird things going on, right? Let me zoom back out of here. Okay, so now we can blink the two. You can obviously see that there's clouds in this image, right? So just by virtue of the fact that there's clouds there, that probably gives away that it's a worse image. But maybe if we zoom in, maybe even the stars. It's hard to tell, I got to say, with an astrograph. Yeah, you can see the stars are a little worse here as well. And that'll come up in the aperture photometry. The light is ever so slightly spread out. It's not as concentrated. So once again, the signal strength isn't as good. So that's true. And then if we look at maybe some of the faint nebulosity, and I don't know if this will show up on the recording, but there's some faint nebulosity here. It has a much better contrast in this image, which is the reference frame, compared to this image where it almost disappears into noisiness, nothingness. So true enough, I agree by my iBrain that NSG has done its job. But what I want to show you is something really remarkable. I'm not going to combine this because I'll show you the combined result in the blue. But what I am going to do is I'm going to combine this image right now with the normal method, because I want to show you what the weights were when you do it normally, not with, see, I'm going to use noise evaluation here. I'm going to force it to tell me what the weights were. Sorry. So this probably, this probably used this one, doesn't matter. And then that's scale plus 0 offset. So this is the normal default way that you run this tool. Although I've been wrong. I need to do it on the original data, not the NSG data. Hang on, let me do it the normal way. Sorry. Let me clear this. I need to add the normal data, not the NSG data. That's this stuff. Oh, I would need to match those files, don't I? Okay, I won't do it that way. I will show it to you in the way that I was going to do it. I have to open up the same files, and that's going to be hard. So let me show you the results that I did when I did the blue example, which is here. So the blue example, I had like, I don't know, 70-something frames, 75 frames or something like that. And here are the results here in the blue. Just like you saw on the screen, the NSG gives me the weights, the values. And then I also did it using image integration. So for every file, noise evaluation gave me a number. And what I can do is I can compare those two numbers to one another. What did it say one frame was compared to another frame? So let me just do this really quickly again. I'm going to show you what is definitely the worst frame here somewhere. Somewhere here I have a really bad frame. So this frame looks really bad. Do you agree that it's again June 12th, number 3, looks like a really bad frame in blue, right? So notice what it says the weight is here. It says it's 0.142. So if I go over here and I compare the same thing, that was June 12th, right? So if I go June 12th, and this was a 480-second exposure, I'm going to go find it. And this was, I said it was number 3. So let me find number 3. So that's number 7. number, what is that? 2, 3. And is this the 480? Yes, it is. So here's the point. NSG says the weight is 0.142 compared to the reference frame. Noise evaluation says it's 2.2. Noise evaluation, image integration says that that frame is twice as good as the reference frame. But we can compare the frames by eye, just as I showed. You can see that one frame with your eye and brain is better than the other. And we, with our eye and brain, agree with NSG, not with noise evaluation. That is craziness. And now I'm going to show you a plot that I don't think is known. I don't think it's publicly known, but I went through and I did value for value, frame by frame, matching what NSG calculated and what noise evaluation calculates. So here is that plot. It is here. And I hope this oppresses the pants off of you, because this is not right. There is something wrong in the world and it needs to be fixed. That's my opinion. So what you see here is that the blue line is what NSG calculates for the weight. You can see that it starts with a weight of 1, and then it goes frame by frame calculating these weights. And then noise evaluation is the orange line. Every time, it almost looks like a mirror image. Every time the weight goes down, probably because the stars got blurrier or the sky got a little brighter or whatever it is, the normal stuff that happens when you image, the weight assigned by noise evaluation goes up. It's perversely wrong. Almost every time. Every time the weight goes down for NSG, the weight given by noise evaluation goes up. And that means that when you average all of those frames together by default, you're not getting an optimal image. And that, to me, just drives me crazy. That just makes me insane. So this graph in and of itself, I hope that you can see the reason why I'm so animated about this idea of getting the weights right, because the weights, in addition to properly doing the rejection, the weights ultimately contribute to the best possible quality that you're going to be able to get for an image. Signal to noise, everything, all of those admirable qualities you want in your image come about by getting that right. So let me now show you some detail. Here are the rejection. Let's see if I can do this. Hang on, that's the wrong one. I did the rejection in B, and here's the rejection in B, right. So here is no NSG. This is when you just combine them in image integration. And this is with the noise scale gradient. And what I want you to do is look at the satellite trail. Because you compensate for the gradient in an image, it means that there is a better match between your reference frame and the frame that you're looking at. And so when you combine all that information together, the rejection is going to be better. It's easier to find outlying values. If I blink these two, do you see that in the image, this says NSG rejection. This is with the noise scale gradient. Do you see how the satellite trail is thicker? Notice here, it's a little bit thinner. Do you ever notice how satellite trails just don't seem to reject cleanly sometimes in your data? They still leave a little ghostly trail. Guess what gets improved when you use NSG? That's what gets improved by taking care of that gradient in the background. By matching the gradient, you get better pixel rejection and therefore a better image at the end of the day. That is as important as anything else that I think I could show you on the screen. And then what I also want to show you is another kind of edge case, but it's really, really cool. Let me just show you this particular edge case here. I had data of NGC 3310 here. And let me see, how do I want to show this to you? I'm going to show this to you in the following way. I'm going to actually navigate there. I'm going to go to here, here, here.
Adam,
Yep.
a question came up, and I think you're probably going to get to it. But when you do your image integration, then you select the weight that was developed by NSG, or is that done
Yes.
by default?
Yes, yeah. So I am going very fast here because I know I don't have a lot of time, but that's correct. When after the conclusion of the script, it automatically brings up image integration for you. And what will happen is, let's see, let me see if I click the correct one here. And what will happen is, there we go. It will automatically populate all of these boxes. See how it turned off? It says no normalization here. And then it puts in weight keyword and weight. So that's different than the default way, right? So it sets up image integration for me. All I need to do is press the button here to do it, and it'll integrate my images. But you're correct that it needs to put in the weights that are generated by NSG, and it does that automatically for us.
So it changes the fits header to include a title called N weight, and then when you go for integration later, it says, you want to use that one?
Yes.
Okay.
Because that's what it says here.
Rejection criteria. I see you got some rejected subs.
Yes. So the rejection criteria is, this is in, let me just show you where that is. That is here. This was actually one of my suggestions to John. John Murphy, by the way, I didn't say, I should have said, is the brilliant person who created this script. And I connected with him the moment that I knew of its existence, because I knew this is exactly what I've been waiting for years for PixInsight to have, because I knew that noise evaluation was just not doing what I wanted. So down here, you'll see that there is a minimum weight percentage. You can change this. Originally, I guess people complained. Originally, I suggested that this be set to 50%. Basically, what this does is that this will, when you load image integration, as you saw there, any frame that is less than that percentage, meaning the scaling factor effectively, you had to multiply by more than 2, is what I suggested. You should probably know about that. It doesn't mean you have to not include it. It's fine to include those frames because they're going to be added in for what they're worth. But you might want to consider that really, really poor frames are more noise than anything else, right? So the poorest frames, at some level, you're going to have to pick a threshold. And right now it's set to 25%, that's pretty poor frame. But I think 50% is a really good threshold to think about. Really look at those images and make a decision if you really want to include those in the average of all of your frames or not. This is a really good way, by the way. I don't think that people ever knew what the relative quality of their data is like. A lot of people were seeing all these red X's show up here. And what that really says is there's a large spread of quality in your data. And you really need to look at that and determine whether you really want to include those frames or not. So that's one thing, is that this will open up people's eyes to really appreciate the difference in data quality within a particular set that have been acquired. For example, you could have one great image and 20 really poor ones, and it'll look like all 20 got X'd out. Does that mean you can't do anything? No, of course not. You can still average all those frames, but you still need to choose that threshold that you want that quality to be at.
So if you get to the end of this process and you find out your selection was a 1, but there were a number of frames that were 2s and 3s that were much better, should you go back and do it again and recalculate? No,
you won't get a different answer. The answer will be exactly the same because it's a relative thing. If you did it again, the frame that had a 2, because your reference was a 1, will get turned to a 0.5, right? And then your new reference will be 1. Does that make sense? So it just inverts the value. There's no difference in the relative quality between the frames. That doesn't change, right? Mathematically, it's still the same.
But the frames that might be automatically rejected might change.
No, they would not. Think about that. You got to think about that, because what this is choosing is it's based on the best frame. When you see that minimum weight, it's not based on the reference frame. It's based on the best frame.
And Jeff was asking, still using large scale pixel rejection?
Sure, that's just a rejection method. That's fine. You can increase your, you can do that if you want. That's another computationally intensive thing. It's usually not necessary unless you have some particular, super bright scattering light event, like if you had a really bright satellite trail, perhaps. But I might argue that you might not need that as much as you might have thought it used to be, right? That things wouldn't reject as well as they can under normalized scale gradient. So you should try normalized scale gradient, maybe discover that you have to use large scale rejection as often as you did in the past.
And if you're doing, I'm sorry, does this change what integration method you're going to use in image integration?
No, the logic for image integration is still the same in terms of number of frames. That statistics determines ultimately perhaps what rejection method you use. Is that the question? So,
yeah, so if you're using generalized extreme studentized,
and I'm using that here because I have 75 frames. That wouldn't change either way that I would do it. That's right.
Adam, would it be fair to say in relation to the questions that Eric's talking about right now that basically the image integration process remains the same and uses the same criteria and everything else, except for one thing, how things are weighted. And now you've got a better way to decide how things are weighted. Is that
it's almost right. There's another part though. Because the normalization process done through NSG results in frames which are better matched, when image integration does pixel rejection, that's this part here, that's also improved. You don't change anything about it, but the result...
I don't change anything, but it changes how it operates with the...
It's not that, the math is still the same, but you get a better answer because the input data is better.
So all these questions that would come up with, do I have to change the rejection algorithm? Do I have to change the this and the that, the other thing? All that stays the same.
All that stays
the only thing that's changing is the percentage of, or is the weight. And now I've got a new factor to determine the weight that comes out of the keyword from the process I just did.
Yes.
Okay.
I'm not gonna argue. Yes, I'm just gonna say yes.
Okay.
And at the end of the script, it automatically opens up and populates the image integration. And
that's right.
Whatever boxes it thinks needs to be checked.
Well, not that it thinks. It's going to be the same every time. It's going to set this to no normalization. It's going to set this to n weight. And it does that in both areas because of the way the script works. The way image integration works, it has two different normalizations. For under pixel rejection, again, it sets no normalization there as well. So that's it. That's right. Okay, so let me just show you a cool thing. I know that I'm going a little bit longer than I usually do. This is a technical topic, but one of the other benefits, this is really a spectacular example. I'm going to, yes?
By the way, Adam, this is just the kind of thing that we all love. So,
and the other thing is,
to the end.
And the other thing is that it's an off day for everybody, Labor Day tomorrow. So no, actually, the fact of the matter deep down inside is we don't have an exact schedule here. So you do this as well as you want to do it. And if for some reason Adam Block has more he wants to say, I think he could probably get on the program again sometime. So
I know.
Okay, enjoy yourself.
All right, so let me just show you this cool example. I need to show you a few frames though, and that means I need to go into wherever I was here. No, go to calibrated light, registered, yes. And then I need to show you star clear star, yes. And actually, let's do star clear star .xisf there. And then I will show you a few frames here. I'm not going to make a big deal about that. But I will make a big deal about this because you'll probably be impressed with that part there. And then I also want to open star room star. There they are. And I'll open up a few frames here just to give you an idea. This is another example where I have a data set that I took across years apart, 4 years apart actually. So I had some data on this thing, which is NGC 3310, which is a spectacularly weird galaxy. Beautiful galaxy, interacting, has all kinds of streams and loops and things coming away from it. Has a bright star in the field, making it a very difficult and challenging object. But between the 2 years, they are very different. Number one, you can see that because of all kinds of problems I had with flat fields and things, check this out, that in the data that I took, and I have lots of data, right? I actually took images that didn't have very good flats and I included them in the data. This is using another technique that I showed on this show that I called selective rejection. And you can reject all of these problems in the image by painting things black, and then it all works out when you combine, again, in image integration. But check this out. You see, the other set of data is rotated because, you know, whenever I took it some previously 4 years ago, the frame is rotated with respect to the more recent stuff. Now they're registered, but now because of the registration, the frame is some odd angle of real information and then black elsewhere. If I took this data before normalized scale gradient existed, and I can't demonstrate this now because the data set's very large, but if I added that all together, I would be left with these triangles of slightly different brightness bits of sky, because the fact that there are these gradients and differences between the images that are not matched, it will not properly make these divisions that you see here, these regions, just won't match in the final combined result. And so you would end up having to crop the frame. But check out the result that I generated using NSG. Now, I first just look at the top left quadrant. I'll explain why the other quadrant isn't perfect. But in the top left quadrant, you can see that you can't even tell that there was a rotated set of data there. It looks like it was a natural, just combined imagery. The reason why there's a little bit of an artifact here in the top right is because of the original data that I took years ago. I believe I did it in CCD Stack, and CCD Stack adds to the edges of images where they overlap. Instead of adding black, it actually adds gray values, the median value of the image. And that's why there isn't perfect rejection here, but that doesn't have anything to do with normalized scale gradient. Actually, the brightness across the image here matches very well, as does down here. It's only in the bottom right. You can just see where, and that's because of the scattered light of the star, that it's difficult to match the gradient there, that you can see a hint of an artifact. But that is just crazy remarkable that I could take data from 2 different complete times, rotations and everything, and now make things work. And I will also put in a plug. This is an excellent segue to a plug for another script that John wrote. If you understand much of the conversation tonight, he has another script that's called, I forget where it is, but it's a photometric mosaic, his photometric mosaic script. And that script, do I have a mosaic thing here? Or is it just under, I forget what it's under. Help me out, someone. Render?
It's under mosaic, I believe.
It is under mosaic, there it goes, yes. Photometric mosaic uses the same basic tools for calculating the scale and everything, but between then different frames, so that you get that very nice matching that I just demonstrated, although it's in a single frame. You can take advantage of this in multi-frame, in a mosaic of images. And I have done that, and it works very, very well. In fact, the most recent image that I've worked on is an image of, let me get there, of M77. And that same matching really, really helps. This is a 2-frame mosaic of M77. And these frames were very, very different than one another. They had different qualities and everything. But somewhere here in the middle that you can't detect, there is the blend, if you will, and the matching of those brightness levels because of the scaling factor and everything, the gradient spline and so on. that is being calculated through these algorithms that John created. So it's really a remarkable tool. So I'd encourage you to check that out as well if you're into mosaics. It uses the very same ideas.
Yeah, I can interject, Adam, that I've used it before, and I think it's great. I've
Yeah.
used it a couple times. It works really well.
Yeah, it works well, and it has a lot of ability to, like you can see in the script, to make some of these adjustments. So before I leave the topic, does anyone have any questions about this plot? Does it make sense what I'm trying to show here? Because this is the most persuasive thing. This is the whole reason I wanted to come on tonight, was to show this plot. Because I think if nothing else, it really shows why it's important to understand this idea of normalization. It really does matter. One of the funny things about image integration is that normalization is part of the black box of what it does. You don't get to see the normalized images. One of the cool things about what I've done tonight, and I didn't show you, is that you can see the results of normalized scale gradient. You get to see the normalized images, which I did show you, but you can also see like what it calculated. I didn't show you the gradient little thing it calculated. I'm sure you can imagine what it looks like, but I can go ahead and do that really quick here. That's here, Draco, Nebula, and I did the red where I outputted one of these gradient files. So here is an example. Let's see. I swear I did, but maybe I didn't. NSG gradient. Oh yeah, these are the gradient files. Here it is. Oop. Let me make it a little bigger. There. So that is one of the frames where it is calculating the gradient across the frame. This is what is matched or being matched in order to make it like the reference frame. So this is actually the gradient that was in that original frame that then needs to be somehow hammered into match the reference frame very well. So it's just a remarkable thing to be able to even see this kind of output, much less the normalized scale gradient output. You don't get to see that as part of the image integration process. And one of the things that I've always thought important is to be able to see those images because they are diagnostic. They also help you understand exactly how pixel rejection works. You can look at the normalized images and you can watch how pixel rejection actually does its job. That's not something you get to see here when you just use image integration. You just get to see the output. You don't get to see any of the innards, which sometimes can be helpful. I'm not saying it's what you want to do every time, but if you want to try to explain to someone what's going on, it sure is helpful to be able to see that stuff.
So what do the PixInsight developers or Juan think about your graph?
I don't think he's seen my graph. Yeah, I don't think he's seen the graph.
Adam,
yes.
That one little square that you just showed us, that grid, when you showed us earlier an image with the red grid lines across it,
yeah,
that little picture was in one of those red squares. Is that what you're saying?
No, I'm saying
Okay.
that gradient is the sum of all of those squares, of just the gradient part, because we know that the signal is the same in both images in each square. So what remains, that difference between the two squares in the reference frame and your frame, that what remains is the gradient difference, and that's what's being matched.
Okay.
I'm sorry, go ahead, Alex.
The size of that picture you just showed us, how many pixels was it? By how many?
It's small. He doesn't do it to the same scale. He just outputs a smaller image.
It's just to give you an idea of what
Yeah.
what compensation they had to go through. Okay,
Yeah.
thank you. Eric, go ahead.
Yeah.
So when you get to the end, you have an integrated image. By this method, your gradient that you have to correct for is going to be likely simpler and easier to compensate for.
That's correct. So this is here. This is the NSG input data, and then image integration combined everything. So you can still see the gradient. This gradient is from the reference frame. It didn't go away. It's still there, but it's not a combined gradient. in my video, I have a much better example. So again, I highly recommend, please watch my video. It's more organized. And I think I demonstrate a few other things better. But one of the things I show is that, and I can show this to you now, but I don't think it's quite as dramatic. So here's the version that you get when you don't use normalized scale gradient. If I blink the two, you'll still see kind of a similar gradient, although you'll see that the normalized scale gradient result actually has better contrast. I don't know if this will be easy to see here or not, but I'm just going to show you just the nebula here. And that's just because there isn't as much other gradients adding in. There's just one gradient that you're matching here. Yeah, that is hard to tell. I'm going to zoom in here. Can you tell that, oh, sorry, that one of these is brighter and a little less noisier than the other? I know this won't come across, but I do have a good example in my in that video showing exactly this very well with another nebula.
I can see it in the meeting room. I'd have to wait 15 to 18 seconds for the delay to see it on the
this isn't a good example, but
I suspect it's not going to be as dramatic on YouTube as it is in the Google meeting room.
Right. So what you're going to do, just to follow up on Eric's question, I mean, what you would do at this point, not digital development, is you're going to use DBE here. And I will just do this very quickly just to show that you get a nice result because the gradient is relatively simple. So I'll do 10. I'll do the most crazy, thing here. I'm just going to place a handful of samples. See, I'm avoiding stars. That's good enough. There we go. That's probably fine. That's fine. That's good enough. I don't care. Do you see how careful I'm going here? Do this, do one here. I'll even try to take care of this thing at the bottom, like this. There we go. Let's put another one here. Okay, how's that? That didn't look very careful, did it? We'll do subtraction, say go. Here is the model, and here is the result. And you can see now, actually, that after you remove a lot of the gradient stuff, it's much easier to see the dust and things finally that's showing up here. I'm going to try to make this look a little better. Here. Go like, it's not tracking. Thank you. I don't want a perfectly black sky. So if I do this and match these two, and we blink. Oh, I guess those were matched. Those were matched? They didn't look matched to me. Let's do that again. Okay. So yeah, with the, once you remove the gradient and then you apply a much brighter display, you can see the nebulosity is going to be available to you. It's very, very faint. But there is some dust in this region, which is what I was going for, was trying to get this dust and stuff. Now you can start to see, some detail in the dust. This would not be possible if you didn't remove the gradients well. And of course, the fact that the gradient is simplified only helps things. But also important is the fact that normalized scale gradient is providing us an image that doesn't have as much noise, and that's going to make it easier for me at the end of the day to render all of this faint, dusty stuff that's in this image. That's pretty cool. Look at that. This is the first time I'm seeing it. I didn't bother yet to even look at it. And this is in blue light, so I'm hoping that, in the red light, it's even better. We'll see.
So do you think this is IFN or the LBNs?
Yeah, sure. This is the flux nebulosity, just dusty stuff floating around out there. Yeah. So I think that is going to be my talk on normalized scale gradients here for this evening. I wanted to get across the idea of, how important normalization is. I wanted to get across the idea that there is a measurable difference between them. It's not so easy to do it in this form, to blink images and show you the difference. I numerically showed you some differences by my plot and numbers and things like that. And I think you should give it a try if you haven't started to incorporate this into your workflow yet. I think it's a really great tool to take advantage of. Please do watch my video, though, on YouTube, where, again, I still think I did a better job here on these videos.
Okay. Thank you, Adam. It's always wonderful to have you here. You certainly think about this stuff and present it very, very well. We do have,
Alex, we do have one more question.
we've got a couple more. Yeah.
Sure, yeah.
Randy Rowe wants to know if anybody can, you use Drizzle after this script?
Not at the moment. So if you want to take advantage of Drizzle requires that you're not you're not registering the images, right? NormalizeScaleGradient, its input is registered images. So unfortunately, at the moment, you're going to have to pick between drizzling and NormalizeScaleGradient. I know which one I would pick. But in the future, the developers, both Juan and John, are aware of this, and they want to incorporate the drizzle as part of this routine where you're not going to align the images permanently and still calculate whatever you need to calculate to get the scaling factor, so that drizzle will do its job. So I don't know the internal mechanism of how they'll go about doing that, but I know they want to incorporate drizzle so that you can still take advantage of NormalizeScaleGradient. But right now, no, because the input of NormalizeScaleGradient is registered images, and you use the unregistered images to do drizzling.
And many of us use the batch preprocessing script, the weighted batch preprocessing script.
Yes.
Can this be incorporated in that at all? And
well, it's not incorporated in the sense that when you use the weighted batch preprocessing here, your output from WBPP this time, and this is actually what I set up right here, is just to do the registered images. So you don't want it to automatically combine, right? And it's not running NormalizeScaleGradients in any way. You have to run it on each of the filter groups, or if you have a one-shot color camera, you can just do it on the set. But your only output from WBPP is up to the point of registration.
And already many of us, use it for part of the work and then just take the output from there to go someplace else.
Yeah.
Okay. And we had one question that isn't exactly related to your presentation from Gary EMC squared, or Gary.
Yeah.
Anyway, how does using CCD stack compare to using PixInsight? You had great success with CCD stack for years. So what's your thoughts now? Well,
CCD stack is a wonderful, simple, very concise program. It doesn't have nearly the number of tools that PixInsight has. It doesn't have a background modeling thing. It doesn't have a number of things. Even this normalization that is now as part of this script, the way that it works or worked in CCD stack when you normalized images was before NormalizeScaleGradient was actually better than, in my opinion, noise evaluation here, because I've demonstrated why. The way it worked in CCD stack is that you would actually, with your eye and brain, you would select an area of signal, and that's how you got the scaling factor, and you would select a background area in these registered images to have a single value add or subtracted from every image for normalization. And we know, of course, that isn't going to be as good as what we're doing here, right? What we're doing here is not a single value, but we're actually matching gradients, which is that's on another level entirely. So CCD stack is a fantastic, simplified stacking software. It doesn't do anything more, though, than really just the rejection, the stacking stuff, what effectively calibration all the way up to image integration does in PixInsight. But it doesn't have nearly the number of tools that you can work with the data now that PixInsight offers. So it is only a subset, if you will, of what PixInsight has.
And just to be clear on that issue of drizzle versus the new script,
Yeah.
you would prefer going with the new script for noise evaluation, and
I would, because
cancel drizzle for now.
Okay, so I'll give you my opinion about drizzle. I see a lot of people drizzle because they can, not because they should. One of the tests that you should do before you drizzle your data is just use normal, go through normally, register your images, make a combined image, upsample that image by 2. The final image, just upsample it 2 times, 200% image. Now go and do your drizzling, all your drizzling work, right? Make another version of this image that's drizzled that you upsampled by 2 through the drizzle process. Now take those 2 end results and blink them. Can you tell there's a difference that mattered? If you can, then drizzle is right for you. If you can't, you had no reason to bother doing it. Most people's data, I would argue, is not really good enough to do drizzling. Drizzling, you need a lot of frames, and they need to be high quality frames at that. And the benefit for drizzle is that you can take advantage of this this kind of extra information that you get through the process of spatial information to make tighter details in images, but it comes at an expense of needing this higher quality, this better threshold of input data. And I think that a lot of people just don't have it. So I was working with someone who had a problem, just image solving their frame because they had upsampled it, because they had drizzled it. And it turns out that their frame, they couldn't do it because, their stars were kind of big, elongated, blobby things. And so it's hard to do a plate solution on that. And upsampling it through drizzle, I mean, that's not the kind of frame you ever would have drizzled. There's no benefit. You're not getting any spatial extra information. So it only made it harder on the person to do what he wanted to do by having this huge 8,000 by 8,000 whatever pixel image that he was trying to plate solve. It took him forever only to fail. That kind of thing seems Pyrrhic at best.
So, I mean, let me put in a good word for drizzling, because I do it all the time.
Yeah.
And I usually have a lot of frames to work with. So in every case, the stars are rounder, the eccentricity is less, the SNR is significantly increased, and the full width half max is slightly worse, which is what you would expect. And it gives me more detail. Now, you got to have 40, 50 frames to make this worthwhile. And you're right, they all have to be decent frames. If you took your normalized data and you did a subframe of that and registered to those subframes, couldn't you do drizzle then, and wouldn't that have a similar benefit?
No, because you've destroyed, when you register a frame, you're destroying the ability of drizzle to actually do its job. Drizzle requires those small shifts between the frames. When you register the frame, you're smearing the light out through interpolation. You're actually blurring your image, which, by the way, now I'll add that if you do take that final image to counter your point, and you use the upsample method of, whatever, could be bicubic or, whatever you do to upsample your image, you're going to get rounder stars there as well. You get rounder stars just by upsampling, depending upon the method that you use. So rounder stars is not a case for drizzle. Detail is, if it matters. But here's another important point. Like this frame here, or some fuzzy nebula, right? Sometimes the nebulosity is just smooth. There's no detail there. Why drizzle? Why not just do a normal thing and then upsample it? There's no detail to be gained by trying to take, I'm trying to think of a fuzzy nebula that has really no detail. It's just kind of fuzzy. I don't know, whatever. Pick some nebula that doesn't have a lot. It's just a smooth glow. So there are some objects that, although you could drizzle, you have enough information to drizzle, the object itself doesn't have any detail that's going to matter. So I think the threshold for drizzling is higher than a lot of people appreciate.
It was my understanding that drizzling was for undersampled data, and if it was critically sampled or properly sampled, that drizzling has no positive impact anyway.
That is an assumption. Yes, I am assuming that we are talking about undersample data. That is true.
Okay, are there any more questions out there, anybody? I want to thank Adam for being here again. It's always great to see you, Adam, and you can come back anytime you want. Just tell us you needed to get on and tell us about some new hot stuff that you found out about. We really appreciate it. Okay.
So please, thank you. Please visit the website, atomblockstudios.com. Visit the YouTube channel where you'll find the free videos if you're not a member of my site, so you can find more information that will lead you to more interesting things. And I'd love to have more eyeballs. So any of the, the eyeballs that are already subscribed to this channel, please parallel your subscription with mine.
Thank you.
All right.
And I think that brings us to a close for tonight. Remember, next week we've got coming back, we've got Glenn Diekman coming to tell us about how he gets his great images from the city, from the suburbs, Los Angeles. So hang in there with us on the Astro Imaging channel, and we'll see you again next week. And let's see, Terry, congratulations. This is Terry's second try with the streaming software, and he's in charge today. So thanks, Terry. It looks like it all went perfectly.
Yay,
So good job.
Terry.
Yay for Terry.
Yep.
And you're in charge, Terry. Take us out.
Okay.